Hello, everybody, and welcome to We Measure the World, a podcast produced by scientists for scientists.
The interesting thing is we finished a project that we put cover crop in instead of fallow. We broke the field into thirds, and we looked at the winter wheat crop following that. And the idea is, well, the cover crop section of the field will actually have more water stress on the winter wheat, so the winter wheat yields after the cover crop should be lower. It just so happened we had one of our biggest droughts after this cover crop experiment. And I started looking at the response. The cover crop, the winter wheat after cover crop was more vigorous. You could actually see it in the satellite imagery quite clearly that the NDVI was better, it responded sooner. Those soils that are more organic carbon rich, they've actually, they have a more cover and they're more resilient to heat stress. They probably infiltrate more water, so they probably actually, even though you might have a crop growing, they might have more infiltration. And they might be more resilient. Those soils might be more resilient, particularly in extreme years.
That's a small taste of what we have in store for you today. We Measure the World explores interesting environmental research trends, how scientists are solving research issues, and what tools are helping them better understand measurements across the entire soil-plant-atmosphere continuum. Today's guest is Erin Brooks. Erin is an agricultural engineer and professor in the Department of Soil and Water Systems at the University of Idaho. He obtained his bachelor's in agricultural engineering with a soil and water engineering emphasis at Washington State University, and then went on to get his master's from the University of Minnesota and doctorate from the University of Idaho, both specializing in hydrologic measurement and modeling. Erin's current research focuses on the management of ecosystems through the combination of field experiments and modeling. And today he's here to talk to us about his work in the fields of hydrology, environmental engineering, and agricultural engineering. So, Erin, thanks for being here.
Well, thanks for having me.
So today we wanted to talk to you about all of your various research interests, but definitely we want to start out with your background. And we want to know how you got into this intersection between soil science and hydrology and modeling.
Yeah, thanks. So as growing up, I was actually had a lot of exposure to both my mom and my dad's side of the family had both agricultural and forestry backgrounds. We both have farms, and my uncle was a dairy farm, which really kind of got into agriculture. And my dad was a math teacher and had his summers off, so I just got this love of agriculture. And my mom said, don't go into dairy farming because you'll never get married and you'll be tied to the farm. So I figured I was good at math and I liked agriculture and got me into ag engineering. And really kind of that background, I think, really drove me. I really wanted to be connected with practical agriculture and forestry. I love, fly fishing, hiking. I love that nature. And for me, the passion of what I do is really applied science, trying to take science to make agriculture, forestry, some of these industries economically viable. At the same time, we can do this in ways that preserve the environment and preserve and make what we have here sustainable and actually available to the next generation. So that's kind of my research, really applied research, trying to make decision support tools from modeling side of things and have it really well grounded in the landscape itself.
Right. So was there any other specific, triggers or crossroads where you're like, I should go this way as opposed to that?
I got hooked up early on at Washington State University in being the ag engineering. I worked a lot with Claudio Stockel, who was at the time actually working with Galen Campbell on several projects and developing a crop system model. And I just got hired on as an undergraduate just to help out his research projects. And it was just fun to go out and at that time looking a lot about evapotranspiration in the field and using instruments to track that. And I just got a love for research and found out, once you graduate, there's research assistantships out there that actually pay you to continue to do this. And so I kind of fell in love with this idea of this, experiments and applied research to solve problems. So that's kind of what kind of drove me into it. And I think for me, the direction it took is really when I got my master's, and I spent a couple of years at Cornell working with New York City's drinking water supplies when GIS came out. Right. And so geospatial modeling and targeting prioritization. And I continue to do that with some of my models is let's target where the pollutant load is coming from. And oftentimes we talk about 90% of the pollutant load comes from 10% of the land, or 90% of the pollutant load comes from 10% of the time. And so really, we have a lot of opportunities to target management to get the biggest bang for the buck, and really, here again, getting back to this applied science.
Right. Well, I think one of the cool things about having you on is for our podcast, we like to hit lots of various subjects. We have a broad, diverse audience who are doing everything from civil engineering to agricultural research, or even farmers and growers themselves. And you've touched on a little of all of those. And so I think first maybe we can hit your research into water balance studies and kind of what got you into that and what you're looking to solve there.
Yeah. So originally, like I said, getting into environmental problems, the first thing you look is in the stream, and so you got some pollutant load coming in, and when I was in New York, it was looking at phosphorus loading, or actually cryptosporidium. Here in the Palouse, it's still nitrate loading. Sediment loading's always been a big topic here, and so when I got into this, there's a lot of understanding studies where we actually put instrumentation in a landscape to understand not only the what's coming out of the outlet of whatever catchment or watershed or even field we have, but actually where it's coming from. Because if you want to start doing geospatial targeting, you want to know both distributed response, where it's coming from, and what's at the outlet. And so a lot of my studies have a lot of them have involved stream flow measurements or edge of field runoff measurements, and then couple that with point measurements, targeted measurements in the landscape where the soil moisture or water level, perch water level fluctuations. And so one of the projects is I've been really excited in the last several years. I work here with the USDA ARS in Pullman on a project on what's called the Cook Agronomy Farm. And this is the LTAR site, the Long-Term Agro-Ecosystem Research Site. And USDA has really invested a lot of money into long-term studies. And we want to look long-term impact of, our soils are changing. pH is changing, organic matter is changing, and we're changing the way we farm. And so there's really important to have long-term monitoring. And so one of the projects I'm really excited about now is a project out here, just a couple miles from here, halfway to Moscow, where we've put in some surface flumes to look at surface runoff. We actually have flumes that we've put in on drain tiles. There's subsurface drainage around here, and then also we put in weighing precip gauges and soil moisture sensors, and then we have some paired catchments out there that we're looking at no-till versus conventional till, where we have eddy flux tower measurements. And so really, when you start thinking about trying to solve and understand water problems, it's really that water balance you want to get at. That in this case, if you think of water balance, input, output, change in storage, we got precip coming in. We kind of good handle on that. We have outputs in ET, which we have a good idea of that. We have subsurface drainage. We have surface runoff. And probably the only thing that really the remaining component is deep drainage, which is kind of hard to directly measure. But there's actually tools that actually use some of you guys' passive drain gauges to actually look at deep drainage to some extent out there as well. And so it's really been great. There's a lot of investment at the ARS into putting even AC power out there, which opens a lot of doors to actually. One of the challenges with edge of field monitoring is your flumes have ice in them, they freeze up. And so we were able to buy some flumes that actually have heat tape in them. And so they actually, when a storm events happen in diurnal cycling, we have freezing at night, actually thaws the flume out. And so it's been really great to actually see these paired sites and actually have all this together to really look at that water balance. And I know the ARS continues to see that more long-term focus on water balance type studies.
So when you're I guess trying to measure the water balance flux, what are some of the particular measurements that you're looking at? What are the the inputs to that model?
Yeah, so like I say, for flume measurements, a lot of it is water level sensing. So I like flumes because they're structures and I don't have to worry about their rating curves so much. And so trying to have some sort of water level sensor that's reliable, and I've gone through actually either pressure sensors or bubblers, and the USGS on their stream gauges use bubblers to do that. From the precip measurements, in here we have a lot of snow, and so we've done using some of the weighing precip gauge products, but we've also used some of the products that you guys have come up with and some of the atmosphere type of measurements that we're using for the precip side of things. So you tie in water quality on this, so then we also then would tie in electroconductivity measurements. And we actually, with the water balance, we can actually tie those pressure sensors into a data logger, which then we can use triggers to do water sampling. And so we have auto water sampler, so when a storm event happens, it'll trigger this water sampler. And so we've used different brands of these water samplers to kind of get at this event-based sampling. So,
Right.
Yeah.
I mean, you mentioned dealing with water quality there. Can you get into a little bit more detail about some of the projects and research that you're working on in that realm?
Yeah. So a lot. If you've been on the Palouse and come visit, if you haven't been there, we have a very unique landscape. There's a lot of topography, and we've had historically a lot of erosion. Probably one or two of the most erosive landscapes around the world in terms of topography, especially in the 1930s, where farmers came in and started tilling the ground using moldboard plows, plowing up and down a hill, burning their residue. And so we have some of the massive erosion. And so we farm now a legacy of erosion, which is removed topsoil, which has made our toe slopes full of organic carbon, which is great. It's nutrient rich, but our ridge tops are pretty depleted. And so the question is nutrient management. How does a grower go in and actually farm a landscape that's so variable? And we've even done studies to kind of using soil moisture measurements and some of our models to actually kind of classify the landscape as ecosystems. And you really can kind of think of a toe slope in the Palouse as almost like farming a humid landscape. It's, the water table could be within a foot of the soil surface for half the year. There's really so you got this humid environment. Then you think of ridge tops, they're really dry. They don't store a lot of water, and they're wind blown, the snow gets drifted off, and so it's more of an arid environment. So you think of farming. So one of the things the Cook Agronomy Farm was set up to do is actually look at precision agriculture. So how do we vary fertilizers so that we optimize nitrogen so that we're not leading to water quality problems, or from a greenhouse gas perspective, N2O measurements. And so in the process of converting to no-till, so we've done conversion to really low impact tillage, which will reduce erosion down, but that has nutrient impact as well. The soils become more structured, you have more preferential flow. And a landscape where we have drain tiles, you can actually have a water quality. You actually increase your water quality. The soil becomes more organic rich, is more nutrient rich, and the microbial environment actually breaks down the nitrogen into nitrate, and then you start having more water quality problems. So essentially, as these landscapes change, we need to understand how to manage them, and there's good ways, and actually we could actually reduce our synthetic fertilizers down. And so one of the projects we worked on, and actually was early on when you guys were bringing out your passive drain gauges, we said, wow, it would be really great to understand nutrient fluxes, and particularly in these no-till soils. And so we actually put in one of these drain gauges out in the landscape up in the Cook Agronomy Farm. And it's interesting, and I have a paper that will show this, is we put these drain gauges in, which you take an undisturbed core and pull it out, and then you put the coupling on it, and you can put the reservoir underneath it, and the pipe's coming up, so you can sample the leachate underneath. We took that core and pulled it out, and there was, I think we counted 36, pinky-sized macropores. It was just amazing, the preferential flow that's going on in here. And so then we would end up doing is we would measure it throughout the year and say, well, what's the flux coming out, and what's the water quality coming out of it, and some of the nitrate loading coming out of these. Typically for the streams around here, we get 10 to 20 milligrams per liter of nitrogen. We were getting up to 50 to 100 milligrams per liter, and so you could certainly see that nutrients coming down. We actually did a rainfall simulation on top of it and trying to look at preferential flow. And what we found was really interesting. We had soil moisture probes in this core, but when we started raining on it, we could actually see bypass flow going on. Water was bypassing where the soil moisture was not wetting up, but actually getting fluxes down at a 5-foot depth before we actually see this wetting front completely fill up the core. So that was really enlightening. And those first pulses of nitrogen were just really hot in terms of their nitrate concentration. So really kind of using that, wow, some of these landscapes, the structures changed, the nutrients dynamics has changed, and that's going to affect our nutrient load. And it really does open up opportunities for growers to really get into well, I can actually drop my fertilizer, the time in the fertilizer,
right.
and that sort of thing is going on. So,
I mean, I think that's super important. So are those macropores basically from, are they wormholes, or is that root holes? Is it all of the above?
you know, it's interesting, and you can actually see it in some of the pictures, is a lot of those macropores actually had a root going right down the middle of it. And it's kind of known, this drillosphere is what they kind of call the environment around a macropore, is really nutrient rich. And so, worms, is that a legacy of a long time? I mean, if you hear the stories around here, and actually it's true, University of Idaho was one of the key ones, is this giant Palouse earthworm that's around here. There's actually papers documenting these wormholes going down hundreds of feet down there. There's actually, it could be a major groundwater recharge mechanism. Yeah. I don't know exactly, but it looks certainly like they're wormholes, and they're going down. I don't know the timing of it, but
that's incredible.
Yeah.
That's wild.
Yeah.
I think, and also just the fact that, like you mentioned, the fact that flow is bypassing the soil moisture sensors. Like they're not reading that flow, but yet we're getting it down, in those drain gauges and those kinds of things. I mean, is that something that is particular to what you were looking at, or do you suspect that this could be happening in other similar agroecosystems?
Right, and I think that the rates that we were applying the rainfall at would be more of it like an intense storm. And so I think those macropores trigger when the moisture content gets high enough. So I think for an irrigated person, if you're applying water as fast as you can, which most people do just to get the water in there, it's possible that you could have bypass flow that's going on. And it's, my background is looking at water quality from watershed perspective. It can be really frustrating then. It's like, wow, how do we model this? How do we capture this? Which kind of actually in the last 10 years, I worked a lot with Dave Huggins and some other agronomists, which we're starting to use remote sensing to actually, from remote sensing, NDVI and NDRE indexes, you can actually see nitrogen content in the crop. Which I said, wow, how many different of these drain gauges I have to put in a landscape to actually document a nutrient load? It would be great if somehow we can actually look at it from a different perspective. And so I started thinking about nitrogen removed by crops. And really, if you start thinking of the nitrogen in the soil, our biggest input is our fertilizer. But if we can actually map the output, actually the nitrogen going to the crop, wow, there's not a lot left. That it's really dependent on the water flux and what's the conditions of the soil. But boy, I can actually start plotting nitrogen use efficiency. And so I started seeing, okay, and this is an index we use with a lot of farmers now. It's like, here we can actually see how much nitrogen removed from your winter wheat crop or your cereal crop, and this is how much you applied, and you just divide the two, removed versus applied, and you have a nitrogen use efficiency index, and you start analyzing your field after a growing year. And it's like, wow, boy, on those ridge tops where they're all poor ground, I'm only using 10% of what I applied.
Right.
And they're really interesting. So I think some of the remote sensing tools, and we've kind of worked with you guys a little bit on your NDVI sensors. I know we've gotten some of the Apogee sensors now. We had some of the SRS ones before, and we've actually put those on center pivots in irrigated areas. Put those on, and actually, as the center pivot goes around, we're actually seeing changes in the crop response and trying to understand nutrient uptake. And so you kind of start looking at problems from, hey, wow, remote sensing tools can really start telling us insights. If I actually finding my landscape now, because I do variable rate fertilizer, is having uptake efficiencies above 50% or 60 to 70%, ultimately, hopefully, the water quality issues go away. And so this kind of, I started like, oh, okay, I can work with these other guys and really try to understand the landscape in a different aspect.
Now you're talking about remote sensing. Have you ever backed out? We've had some folks on here, some guests who have talked about working with drones or even satellite imagery. Have you got into that and working those into your models?
Yeah, we recently hired someone, Dr. Johnny Lee, in our department that really does a lot of drone imagery and using artificial intelligence to try to analyze data analytics, trying to analyze patterns and looking at different wavelengths and what they tell us. And from a practical farming perspective, and I teach a precision ag class, satellite imagery, it's comes every 5 to 10 days. So from like a nutrient management perspective, I say satellite imagery is actually a good tool. It doesn't document the why or in detail of that doesn't have the resolution to document disease, stress. And I think what we've been looking at is using drones to actually fly those a couple times in your field, and a lot of times your patterns in your field are consistent, which for managing a farm, you want to look at consistent trends. Actually taking drone imagery combined with satellite imagery then it helps explain what's going on in your field, it helps link the two and actually helps scale up. And so that's some of the things that we're looking at is how do we use drone imagery, understand these patterns on a very smaller scale, then have that direct maybe soil sampling or direct some tracking to say, well, what can we investigate what that is, and then help interpret the satellite imagery we can use more for more yearly or even in season management of fertilizers or some herbicides or something.
Right. I think that's fascinating. I mean, we could go on all day about this. I did want to kind of back out because you've talked a lot about your work with modeling, and like we mentioned, we have people doing all sorts of diverse research. But also, I wanted to ask you about finding the balance between doing the field work and the modeling itself. I mean, we have people. There's traditions of being heavily reliant on one or the other, and I just wanted to know, like, how do you find that proper marriage between the two?
Yeah. No, it's one of the things I really stress with my grad students is this balance, and what I really like to impress upon them is doing both. I would love to have a project where they're actually out in the field, they're looking at structure, they're looking at actual reality and understanding spatial variability and understanding these preferential flows and really saying, oh wow, this is the processes. I also want them to do modeling because, essentially in the end, if you can be an experimentalist, and it's great for research, but if you're a practical applied, you're going to do problem solving, we just can't measure everything. There's just no way we can get at it. And so you can be an experimentalist is like, well, at some point, if I want to make impact, I need to go to a model. And so that kind of gets you into the modeling side, but then you can get into that pit where everything's a model. I'll take whatever model off the shelf and apply it. And a lot of models aren't appropriate. So having that background of, hey, actually, this is what I see. This is how I see runoff or soil moisture or something going on. And that model's really not appropriate for that. So having that actually some more critique and some understanding of what's going into a model to help you select that model. Models, they can apply them almost anywhere. A lot of the tools and the data we have available, there's really great geospatial modeling we can have. And then you can fall into that trap that, we can do all this modeling. But if you're a field experimentalist, you're like, there's no way a model can predict this. There's no way that a model could capture all the spatial variability I see out here. And so, this idea, and I try to impress upon them in my modeling classes is all models are wrong, but some models are useful.
Right. Yeah.
And so how can the data we collect from experimentals help us parameterize and improve the accuracy of the model? And what's interesting thing is when I start doing modeling, I tie modeling back into, we think this pattern, the model's saying this pattern is happening. Do we see it in the data? And using the models actually help interpret the data kind of feeds back on itself. And so this I think it's a kind of a cycle. It's a feedback thing, experimental to understand reality, spatial variability, uncertainty, then helps us communicate our modeling results because, boy, if that model's going to predict stream flow to the thousandth decimal point, there's no way it predicts that well. Because I know the reality is the variabilities and then the feedback, the data. So,
I think, I mean, do you have any rules of thumb when it comes to model creation or determining success of a model? I mean, there's statistical tools that you can use to to gauge the success of a model, but a lot of times, I mean, sometimes you can visually or you can understand we're getting diminishing returns with this model. We've got too many inputs, too many parameters. We need to kind of dial it back.
Yeah. No, there's a lot of models out there, and with AI and some of the data analytics, you can take whatever data stream, and the model doesn't even know what it is, and you can put some statistical analysis and try to simulate what's going on. That's great if you have one location with a lot of empirical data and you want to continue to do empirical data at one location. So it's almost taking data, but to really understand, well, how does climate change? Well, what is actually converting to no-till, going to affect in the long term.
Right.
It's a lot of these processes that you need to have almost a scientific understanding. So the process-based models, some of the process-based models can get into really detailed too. So I'm looking at air entry potential on a very specific part of a landscape where we don't even know the soil variability, that there's information's not there.
Right.
And so you can have models that are just over parameterized.
Right.
What I found is some of the more simpler models actually can do a lot of that variability. They're understandable to actually stakeholders. And they are providing, and a lot of times all what stakeholder want or problem solving is red, yellow, green. Is a higher risk here, a lower risk there? Spatially, is this more or less? And so sometimes we get caught up in chasing the Nash Sutcliffe efficiency or the R squared or whatever.
Right.
And from applied side, they just need some advice. And I think there's a lot of that these tools can provide. I'm doing a lot with wildfires right now.
Yeah.
Doing some wildfire modeling where we're taking geospatial models and we can upload burn severity maps. And we've been working with Portland for a long time. And just last 2 weeks, the drinking water, where the Bull Run watershed, where Portland gets their drinking water, is burning now.
Oh, wow.
So there's this risk of a pollutant load coming to the drinking water reservoirs, and all Portland gets their water from unfiltered water source. And so if we now have ash and sediment and water quality coming to this reservoir, they want to know, what we can do now? And one of the things you can do after a fire is actually put some mulch or wood shreds on. What we can do with the models, they can say, we can tell just based on soils and the hydrology, this is going to be a high risk of erosion. Fly on some wood mulch here. I mean, that's just something, and if you only have a certain amount of money, this is the targeted prioritization approach. Right. And then we can then come back on more of a probabilistic approach and say, we can run it through 100 years of weather data and actually get, there's a 10% risk that the sediment load coming out of the reservoir is going to be at this level. And so we can actually get probabilistic output. We don't have to be absolute. We know our models can't be, but then it gives them a ballpark and they can make decisions based on that. And so, Yeah,
I mean, there's pros and cons to, like you said, dealing with stakeholders who may not be in your scientific, specialty, or even in any of the sciences at all. Like you're talking about policymakers and other groups like that. What are some of the things that you've learned as you've worked with these interdisciplinary groups on these various projects? I know you've worked on projects with the Landscapes in Transition project, where you're dealing with all sorts of different researchers and scientists who have their different specialties. You're working with this Portland project where you're dealing with people who are not in the sciences at all. What are some of your learnings and findings from your own personal experiences in those?
Yeah, and a lot of it for a while, and there's still a term that's going around, is best management practices. What are the best management practices? And a lot of times we're going into a watershed study. What's the best management practice? And we can, I can use these tools and I could say, this is the spot we need to do. This is the high erosion spot.
Right.
But a lot of times I talk in my water quality class is best management also is social and economic. There's other factors out there that might prevent someone from doing something. And so I think we need to take this holistic view of, okay, what's possible? And we could go in and say, why that part of the landscape should adopt this. Well, this might be someone, a farmer that's maybe farming some poor ground, is not making a lot of money, doesn't have the capacity to respond to that. And so it might not be the perfect solution. The better solution might be working with someone else, maybe not as erosive of land, but maybe has the capacity to do that. And so really understanding the culture of the people that you're working with, what limitations do they have, like nutrient management. A lot of times they're farming big lands, or they don't have the capacity, the actually machines to do some of this. And so trying to understand. I love working with the farmers. Oftentimes I have a project, I feel like I learn more from the farmer than I give back to him or her. And so the more we can understand, this is the limitations I have, and this is what, and I can come back with my science-based solutions and say, okay, let's work together and understand that dynamic. Another example, is I teach an irrigation water management course. And a lot of times you think of it, irrigation, we have tools. We have soil moisture sensors. We have water potential sensors. We have weather stations. We can predict evapotranspiration. So, and then you do surveys of the irrigators and how many people are using that sort of information to irrigate from irrigation scheduling? There's very few.
Yeah.
And it was interesting. It's like, why aren't people using some of these great technologies? And then I want to start having more, I teach to ag systems management, which are more applied. A lot of the kids in my class actually come from irrigated farms. And they start telling me, it's like, our center pivots have a certain capacity to apply water. We can't instantly apply water over an entire field. We're only applying water to maybe 5% of a field at a given time.
As you're passing.
And as you're passing through, it says, guess what? Irrigation scheduling, I turn my center pivot on mid-June, and I don't turn it off till August, and I'm still not meeting my crop water demands. And I started to think, okay. So irrigation scheduling to a person with a center pivot, they have some limitations. And so really the irrigation scheduling maybe is, and what I do believe, and I have a grad student working down in southern Idaho, working with people on water quality implication of over-irrigating, is we can make a lot of ground in the spring. There's a lot of times that growers are over-applying in the spring. They're losing some of their nutrients. We can actually become more efficient there. And that's where I think we can target growers with some of these tools and soil moisture. And so it wasn't until I started getting interaction with people, like, okay, so the solution, this is where we need to target our tools and how we can reach out to stakeholders. So.
Right. I know you've also mentioned that you've worked with, so in particular, we can stay with ag and with crop management practices. You've talked about working with no-till. I know you've done some work with studying cover crops and other things like that. I wonder, especially, can you talk about cover crops? We haven't mentioned that. And some of the interesting findings that you've been getting there. Yeah.
So, just recently in the last year, University of Idaho got a $55 million Climate Smart grant, which I've been asked to help lead with Dr. Sanford Eigenbrod over there, which is a real challenge, but a lot of the project is incentivizing growers to do more sustainable practices, and really for a motivation from a soil carbon perspective, increasing soil carbon and reducing greenhouse gases. And so some of the practices that we really want is increasing carbon is cover crops. There's a lot of great testimonials from the Midwest where they've done some really good cover crops have put in, and that's been really successful. Here in the Palouse, our landscape, our climate's different. We don't get any rain in the summer, which is good for dryland, I guess, just so we don't want to have too much rain while harvesting wheat, but it prevents us with doing some of the fall seeded cover crops. And so, but there's so many growers out there that really see the benefits of cover crop diversification, and trying to build up their soils again. And so there's a lot of people investigating. So this was this landscape and transition project we've done, and actually looked at different climate zones here in the Palouse. We've put cover crops out in places that typically have fallow. So now the growers to the point where they're really willing to put a cover crop in instead of fallow, and which is a risk because that's their water storage for the next crop. And so trying to document some of this. And so that's what we're looking in this project, can we get people to adopt cover crops? And so one of the practical tools and ways we've been trying to help growers in adoption of this is, well, each year is different. If we have a lot of June rains, you can keep that cover crop going. But the question is, when do I terminate it? And so that's just one of the things that we've been working on and I currently have a Western SARE project I'm working with Dr. Sanford Eigenbrod as well, is actually looking at termination of cover crops. And that's one thing I think soil moisture probes and actually irrigation models, so soil water models, we can track soil moisture pretty well in this landscape. And I think cover crop termination has a lot of great opportunities for us to help decision support on those. So but the interesting thing is we finished a project that we put cover crop in instead of fallow. We broke the field into thirds, and we looked at the winter wheat crop following that. And the idea is, well, the cover crop section of the field will actually have more water stress on the winter wheat. So the winter wheat yields after the cover crop should be lower. It just so happened we had one of our biggest droughts after this cover crop experiment. And I started looking at the response. The cover crop, the winter wheat after cover crop was more vigorous. You could actually see it in the satellite imagery quite clearly that the NDVI was better, it responded sooner. And one of the things I think potentially could be happening out here, we need to understand it more, is those soils that are more organic carbon rich, they've actually they have a more cover, and they're more resilient to heat stress. They probably infiltrate more water, so they probably actually, even though you might have a crop growing, they might have more infiltration, and they might more resilient. Those soils might be more resilient particularly in extreme years,
right.
flood years,
right.
drought years. On a common year, you look at, let's say, no-till versus conventional till, or a cropping system more diverse versus other. I think the yields are pretty similar.
Interesting.
But I think, in terms of, we talk sustainability going in the future, climate change, how we restore our soils, I think some of these things we're going to start seeing more and more on these more extreme years. And so, I'm pretty excited about how do we get cover crops to work. When do we plant them? When do we terminate them? And just love to see the growers are hungry for solutions. Right. They really want this to work. And so hopefully the next 5 years as a project, we can start, coming up with some solutions that integrate that.
I mean, that's one of those things where, and we've mentioned this before, is that when we're dealing with growers yes, there's traditions of how to farm and those kinds of things. And maybe they're, stereotypically slow to adopt new practices and that kind of thing. But at the same time, it's our human nature to do that cost benefit, that risk assessment, and say, just mentally, how much of a risk do I dare try this new thing? And then, what if, like, our models could say, oh yeah, you're going to have 60% success, over the 100 years that we've been running this model. But that's a median value, and that's not necessarily going to say, hey, you might have these extremes where you're going to get nothing, or you might have definite success and you're going to double your yield, or those kinds of things. And so being able to I guess my question then would be, how have you been able to communicate with those growers and others to really help them see the potential benefits for implementing these new practices?
I think one of the things that's really changed, and I talk about this in my precision ag class, is the historic imagery, the historic satellite imagery. Now that we can tap into the last 10 to 15 years of what's going on in a specific field. And so what I like to do is talk to my students about is let's look at the temporal stability. Let's look at, and a lot of times I look at a field scale variability. Let's compare the average, you could think of NDVI on this part of the field versus what the average is for the field. And then I just go back in time and say, is this consistently always lower? Is it consistently higher? And what was the best year versus the worst year? We start seeing that. And I think with that understanding, a grower can come in and be realistic about, well, yeah, I understand. 1 year to the next, it could be feast or famine. But from a profitability perspective, should I still fertilize to that great year every year, or should I drop my rates just to say this is more a realistic yield goal, and actually in 9 out of 10 years I'm going to be making more money. Maybe that 1 year I'm going to have nitrogen stress on that part of the field. And so trying to get maybe a temporal analysis to help. I think some of this, growers are hungry. A lot of times growers adopt a new idea and they do it the whole farm. It's like, if this works, I'm gonna do it the whole farm, And what I encourage is, with remote sensing, some of these tools, always be a learner. Set aside, there's so many opportunities to on-farm experiments. And I say, well, try it. Do a trial and convince yourself, and do it over a couple of years, and try cover crops on a part. And so it's not as high risk. You're gonna learn from that and then slowly expand. And I think that's where universities, I'd love to see the universities become more engaged with growers. And some of the things with this new project, we're developing essentially a geospatial farm management tool that we can use from a research perspective, to upload our soil sample points or some of our water quality things. But they actually can access some of the analysis we're doing with the models and some remote sensing data that we can do that maybe they can't do, and maybe then have them be able to go into a tool and help us work together. We can learn from them. This is what works and what doesn't work, and we can then demonstrate very quickly what worked last year. A lot of times the universities have a reputation of, you get this money, they use my field, and I don't hear from them for 5 years. And I think we need to become more engaged with growers in that way. No, we have tools that we can come in and learn along with them. And I think there's a lot of growers that would love for us to engage in that way. And growers know the good years, they know the bad years, and I think talking to them realistically about that, I think using some of these tools is a good approach.
I was going to ask, have you tested different types of cover crop? I was thinking, I mean, there's different types of cover crop. You can talk about forage, cover. You can talk about, or like green manure, or how you manage that cover crop itself.
Yeah. So some of the people, we have a dramatic climate gradient, and so people near Moscow have a 25 to 30 inch precip zone. Mm-hmm. Really, cover crops to them, really a real big benefit for them is actually growing a crop even during the winter, fall seeded cover crops, because we just have so much water.
Right.
And they're let's use cover crop as a water management strategy. Just take some of the water out. Also, it takes that nitrate out and converts it into organic matter, and then essentially, as it breaks down in the next year, then it releases that nitrate back to the crop when the crop needs it. Mm-hmm. And so, I think from that perspective, so it's a fall seeded cover crop. We want to get it in, and we have the water out there. Probably could get it in a lot easier out there. And so that strategy is is a fall seeded crop. I can't have annuals that are going to, not resist the frost. Right. And so then selecting winter peas or something like that can endure the winter. In the dry areas right now, it's water managed. Kind of the example I described before is like, it's really hard to start a fall crop. The soil is completely dry. Germinating anything in the fall is difficult. The only reason we do winter wheat is because it comes out of fallow and there's a lot of moisture there after the fallow. So in that drier area, it's maybe a spring cover crop that they can go in, and they can do it during that fallow year. And then the challenge is the cover crop termination. And so varieties, how many different types? There's mixtures. I don't know. I have a good understanding. I think there is so much benefit to crop diversity, and I don't think we completely understand it. There's some crops that work well together, having the legumes with the cereals, with the brassicas. Somehow there's certain combinations, and the project we looked at with Sanford Eigenbrod and his student really saw under winter peas, the arthropods respond to it. The macro, the pollinators, the insects, all this actually responds to it in a really good way. And so, I think that's the science that.
That's true.
I don't know.
I know that's how do you model something like that? Okay, we're gonna put the arthropod parameter in here, or the pollinator parameter, and that's amazing. I wanted to going back to watershed management. Just really quickly, I wanted to get some more details into, you've been publishing recently on Web Cloud. And so if you could go into a bit of detail on that water erosion prediction project and how it began and where it's at now and where you're adding to it.
Right. Yeah. So this WEP model, so the Water Erosion Prediction Project, it was a model designed to replace essentially USLE or Russell NRCS planners. If you put a conservation practice in there, they need to document what sort of reduction in sediment. It's more USLE, and a lot of it was actually developed here in Pullman with Don McCool historically doing a lot of plot studies, and it's a good 30-year average erosion rate. And so, but it's not a process-based model that understands dynamics or changes in intensity, and so it's not a process-based model. And WEP was one of these models that was supposed to replace that. And it's here gets the politics of, you got conservation planners, not really to, teach an old dog new tricks. It hasn't been adopted completely yet, although we're getting close to that. And so it's a really great model for me. It was understanding, I understand hydrology, landscape hydrology. How then does it feed back into erosion? And the Palouse has gone from a time when we used to have a lot of soil crusting, we have a lot of infiltration excess or Hotonian runoff we like to talk about with a precip's greater than infiltration rate, now to a landscape like no-till, where erosion now is focused in draws and gullies. We have more gully erosion. And so trying to understand that, getting a tool, so WEP was one of those tools that could do both those types of hydrology, and it was great for scientists. And for me, at Moscow, Bill Elliott was one of the people actually helped parameterize the WEP model back in the 80s, actually got a position at the Forest Service here in town and said, we can apply WEP to roads. And so let's take this model. It does a single hill. We can think of a road like a hill slope, and we get road obliteration. So it's a big point in time where can we use a model, look at erosion before and after? What's the reduction in sediment load? And so it started with more of a hill slope based application. So taking a process based model, putting it into a simple decision support tool, and they did a great job of putting web interfaces. So now you can have 3 clicks. This is where I'm located. This is the soil type. This is the steepness of the road. Here's the field gradient. And it essentially takes a process-based model and does a very simple prediction. Do a 30-year, and you can do return period analysis. This is the 20% probability of this erosion rate. So this was a start as a hill slope model. Now Pete Robichaud is now the director there, was really big into wildfires. And so here, post-fire response, what's the risk of this erosion? We know the hydrophobic soils come in. We know that the cover's gone, so the erosion could be massive. And so he took that, well, let's do it as a simple hill slope or maybe a small catchment. And we'll do a decision support tool based on the hydrophobicity, based on the burn severity. What can you expect coming out? And so they have all these hill slope tools. They call the FS web interfaces. You could go online, you can find these. I came in from a watershed perspective and say, man, really is a great need for bigger scale watershed studies. So, which never before had the model been applied other than maybe a couple linking hill slopes and channels a little bit. And so we actually took some of the things we were learning and expanded that out into a watershed based model. And for a while, a lot of the GIS growing up and a lot of stuff early on was ArcView, ArcGIS, and all these. And so some of these web tool, there's people that actually tied in. Chris Rentschler is, developed this GeoWeb tool. So actually, we can use web in a geospatial like ArcGIS. It got to the point every time ArcGIS updated, you needed to update the code to make web work on it. And so we said, man, what if it's just an online watershed interface that we developed? And so that's what we had some really great programmers at University of Idaho that I kind of feed ideas, and they do the magic to create these tools. So now we have this, what we call a web cloud tool, and we did publish that in the last year or two here, that there's a couple companion papers out in the journal Hydrology. Really great tool. It looks like Google Maps. Go in on any point in a landscape, creates a stream network based on the DM, extracts all the soils data. Then you can break out the hill slopes and channels. And take some of the parameterization we have for wildfire. We can upload burn severity maps and then actually predict sediment load, stream flow. There's actually a wet water quality you're starting to work with now that's taking the SWOT model algorithms and put in to do water quality. And that kind of gets at more of the stakeholders. They really want to know the watershed outlet. And particularly as we went forward, they did a lot of work in Lake Tahoe. Lake Tahoe was this place, this great icon. Back in the 60s, you could see down into the water 110 feet. It gradually has declined. So now 50, 60 feet. At the same time, Lake Tahoe had never been logged before. I guess the story goes Mark Twain was the last one that actually had a major wildfire. He had a campfire, got out of control back in the late 1800s. Nothing had been gone in there. And then all of a sudden, wildfires started showing up. They had a couple wildfires in Tahoe, and they said, wow, if we had a lot of sediment coming to our lake, this could really drastically reduce the quality of the lake. And so then this idea of forest thinning came up. Okay, should we go in and thin this forest? And then where should we thin it? And our watershed tools were actually really well geared to forest thinning. And then we could start doing comparisons between forest thinning and the do nothing of leaving it there. And what if there's a wildfire every 20 years? Is that better than thinning every 10 to 15 years? And so that was kind of got into this web cloud and the applications. And we went from Tahoe now we work with Seattle quite a bit. The Cedar River watershed, where you get all the drinking water from, is from an unfiltered water source in Seattle. And they are very concerned about the wildfire scenario. We have NASA is actually giving us funding now to actually use more of their geospatial products to help develop these decision support tools. You could almost do a real-time early warning system type of a tool. And so taking these models and use them as a watershed tool to make informed decisions. So we have now a European version of it. I'm actually going to Spain next week, and we can go in there and actually run watersheds in Spain. We actually, colleagues in Portugal are running. Australia has some major fires. We have an Australian version of the tool now, and so it's great to see how it's expanding and the applications of that tool in particular.
That's super cool. Yeah, that's exciting, and to be able to see that, especially going from something like you said, going from ArcGIS, which I used forever ago, and now just being able to have here a couple clicks, or we're just going to go online, a couple clicks, and we're going to be able to see what we want to see. And so I think that's super fascinating.
I know when I started my master's, I did it on grass, so it was grass. Now it's QGIS now, but also at least that one's free.
Yeah,
so, yeah.
Well, we're getting close to the end of our time. Are there any other projects you'd like to chat about? Any other things you'd like to share with our audience?
Yeah, I guess the one interesting thing ties back to the wildfire, and we've been working with you guys on as well, is kind of looking at the impacts of wildfire on soil water retention, and using some of the hyprop and to look at how does that impact itself. How do we see the burns affect the carbon, which affects the retention properties? The soil texture even changes after wildfire. It's really crazy, and we're actually tying that with nutrients as well. Phosphorus, how is it soiled with phosphorus? And so that's another kind of a lot of use lab-based or kind of we actually burning soils with propane heaters out in landscapes right now and taking samples from as a controlled environment. And so so that's another angle that we've done on trying to understand the wildfire. So a lot of projects, a lot of different things you can go in.
And especially, with those wildfire projects, that's super important nowadays as we're dealing. This is a whole other thing when you're talking about modeling climate variability and those kinds of impacts. But definitely being able to see pre and post fire and those kind of landscape managements and how we can mitigate some of those risks there is super important nowadays. Yeah. All right. Well, I think that's all of the time we have today. So thank you for stopping by, Erin. It's been a great discussion.
Yeah. Well, thanks for having me.
All right. Stay safe, and we'll see you next time on We Measure the World.